Today we explore one of the most elegant ideas in mathematics. The factorial function only knows whole numbers. But what if we could ask, what is 0.5 factorial? The answer comes from a beautiful tool called the gamma function. First, a quick recap. The factorial of n means multiplying n by every whole number below it, down to 1. 0 factorial, 1 factorial, 2 factorial, and so on. But this definition breaks down the moment we ask about a fraction. The gamma function extends this idea using an integral. Gamma of n equals the integral from 0 to infinity of t to the power n minus 1, times e to the minus t, dt. This single formula works for whole numbers, fractions, and beyond. Why does this actually work? The exponential term, e to the minus t, decays much faster than any power of t can grow. So no matter what value we plug in for n, whole number or fraction, this integral always settles down to a single finite number. Instead of multiplying whole numbers together one by one, we are measuring the area under a smooth curve, and a smooth curve can be measured at any point, not just at the integers. That is the entire trick behind extending the factorial. Using integration by parts, we can show that gamma of n plus 1 equals n times gamma of n. This is exactly the same recursive pattern as the factorial rule. Now let's prove that 0 factorial equals 1. Gamma of 1 is the integral from 0 to infinity of e to the minus t, dt. Evaluating this integral gives exactly 1. So 0 factorial equals gamma of 1, which equals 1. Now for the exciting part, 0.5 factorial. By definition, this equals gamma of 1.5, which, using our recursion rule, equals 0.5 times gamma of 0.5. But where does gamma of 0.5 actually come from? Let's derive it properly. Gamma of 1/2 is the integral from 0 to infinity of t to the power negative 1/2, times e to the minus t, dt. If we substitute t equals u squared, this integral transforms into twice the integral from 0 to infinity of e to the minus u squared, du. That second integral is the famous Gaussian integral, and its value is the square root of pi, divided by 2. So gamma of 1/2 equals the square root of pi. Now we can finish the calculation. 0.5 factorial equals 0.5 times the square root of pi, which simplifies to the square root of pi, divided by 2, approximately 0.8862. If we plot gamma of x plus 1 as a smooth curve, it passes exactly through every factorial value at the whole numbers, while filling in every gap in between, including our new point at 0.5. So where does a fractional factorial actually matter in everyday math? Here's a simple example. There is a single formula for the volume of a ball in any number of dimensions, v equals pi to the power n over 2, times r to the power n, divided by gamma of n over 2 plus 1. For n equals 2, gamma of 2 is 1 factorial, which is 1, so we simply get pi r squared, the familiar area of a circle. For n equals 3, we need gamma of 5/2, which requires gamma of 1/2, and we already proved, in our earlier Gaussian integral video, that this famous integral equals the square root of pi. Using that result, we get 4/3 pi r cubed, the familiar sphere volume. And for n equals 4, gamma of 3 is 2 factorial, which is 2, giving us pi squared over 2, times r to the 4th, the volume of a ball we cannot even draw, in a dimension we cannot directly see, computed exactly using the very same formula. The gamma function turns a simple counting tool into something that works across the entire number line. Thanks for watching.